All right. So we're going to do lesson 2.2. This is called single displacement reactions. And this should ring a bell to you from grade 10, I'm sure, right? Whom here did I teach grade 10? A few of you, right? Sorry about your luck. But some of you had Trush, presumably, or Elaschuk, or other competent teachers. So you would have covered this. The people who took it with me will let you know that it was strange. All we ever did was work on our dance moves. Very straight, just every day. It's like, all right, guys, we're going to work on the choreo. But usually, you get these sort of lurid, sort of torrid metaphors when teaching displacement reactions. And so not to disappoint, let's do a metaphor. Let's imagine that somebody is, on a date. As one does, one goes on a date. So here we go. We've got, and we'll be, full 1960s heteronormative, and we'll say, here we go. We got a young man, and he's on a date with a young woman, and we'll be, again, full 1960s heteronormative, and we'll do the stick figure with a skirt, whatever. Okay, let's give us some names. This is Gary. This is Larry. They're on a date. And they go, and where does one go on a date in Welland? I don't know. Where does one go on a date in Welland? You guys got Taco Bell. Maybe Arby's. Do you have an Arby's? Love an Arby's. Niagara Falls has an Arby's. St. Catharines has an Arby's. Sorry?
Arby's is gross.
Oh, okay. Is that technically or just opinion-y?
That's very popular.
Okay, well, if jumping off a bridge were very popular, I wouldn't join in, but you do you. Thank you very much. So, as one does, Gary takes Larry, who are this couple, to the Arby's. And then, maybe you go on a first date to Arby's, and maybe this strange thing happens where behind the counter, you got someone else. You've got Mary. I don't know. And Gary and Larry, they're on their date. They go to this, Arby's. And, this is one of the classic blunders. You don't take your date to Arby's. Do you know why you don't take your date to Arby's? Because you got Mary working there. And that Mary, charming. Charming as the day is long. And then lo and behold, you're there, you're ordering your beef and cheddar with curly fries. Oh, those curly fries. Love those curly fries, right? And spicy, they're good. And you're waiting and you're thinking like your date, Larry, what are you going to order? And you look over and Larry's just locked in, eye contact with Mary. And you discover something. You know what you discover? You know what's true about poor Gary at the end of all this? Poor Gary, all alone, all by himself. And then what has happened in this Arby's? End of shift. Mary's like, hey, I'm off. Larry, what you up to? And off they go together. We used to have Gary and Larry, and now we've got Gary all by himself, and we've got Larry and Mary. And that's what that team is. Why you don't take a date to Arby's, and it's not because it's disgusting, it's delicious. It's a fine, fast, see? Well, there you go, and now you're backpedaling. But the point being, you don't take them because you don't know who might be working behind that counter, and you could be out, man. You could be out so fast it'll make your head spin. How's that make you feel? Now you're crying in an Arby's parking lot. You don't want to be crying in an Arby's parking lot, do you? No, you don't. Unless you do, in which case you do you. But this would be a date gone horribly awry. Yeah, you show up with your partner, you go to the date, there's somebody else there, and before you know it, you're all by yourself. And where's your partner? With somebody else, right? This is the lurid, torrid description of a single displacement reaction. What happens in a single displacement reaction is what happens to allegedly, hypothetically, a teenager in an Arby's parking lot, which is a couple becomes not a couple and a new couple forms. Does that make sense? So if we take this into the general form, the idea with a single displacement reaction would be that you have some compound AB, some ionic compound AB, and it's going to react with something C, And the truth is, it could be the positive ion or the negative ion that switches out. In this case, we'll say that A ends up all by itself, and we end up with C and B together. Does that make sense? Now, obviously, depending on what the cation is, depending on what the anion is, this could be there could be lots of different numbers. This could be A3B7 or A2B1, right? We don't know. That depends on what we got. But that's the generic form of this, right? So in a single displacement reaction, a compound reacts with an element and one of the atoms in the compound is displaced by the element. And what we mean by that is just they switch places, basically. Excuse me, I'm terribly sorry. Does this ring a bell? You've done this before, yeah? Good. It's much easier to actually look at this with examples. Let's say that what we have is, copper 2 nitrate reacts with, and let's say, lithium. Copper 2 nitrate is going to react with lithium. In this case, I've given you half of a word equation. What's the other half of the word equation? What's going to happen to this? We're going to have copper nitrate, and it's going to react with lithium. So that's copper nitrate, right? And that's lithium. On the other side, what's going to happen? What's going to happen? The lithium is going to, Gabriel. Very good. So you'll end up with lithium nitrate as a product, right? And where will the copper be? By itself, right? So this will produce lithium nitrate and solid copper. So if you do this reaction, you should actually get the lithium metal getting used up, but copper metal should actually start forming out of nowhere, which is kind of interesting. So let's take a look at turning this into a balanced chemical equation. Now, the thing you'll note is that those Unit 1 skills, they're not going anywhere, because what do I need a formula for? Copper 2 nitrate. Very good. So I'm going to have to know that we have copper, and what's nitrate? NO3. Does anyone remember its charge? It's -1, yep. And copper, what charge is it? It can take two different charges. It can be +2 or +1. What is it here? Yeah, how do we know that? It's right in the name. Very good. So there we go. So copper, one of them would give away 2 electrons, 2 of them would give away 4, 3 of them would be able to give away 6. Nitrate, when it forms, needs 1 electron, 2 of them would need 2, 3 of them would need 3. What's the formula here? 1 copper, 2 nitrates. Okay, so what is that formula? Okay. It's getting longer.
Wait, no, stop.
Sorry, I'm being difficult. Obviously, what goes in brackets? The NO3, and then there's 2 of them, right? Thank you for putting up with my being a pain in the butt. What's this reacting with? It's reacting with lithium. Good. Now, lithium, is it diatomic? Does that have to be Li2? Hofbrink Li? No. Lithium is a metal. It's going to be a solid. In all likelihood, you usually do these reactions using solutions. So if you do this in water, the lithium isn't going to dissolve. Lithium doesn't dissolve, but the copper nitrate probably will. So that will probably be aqueous. That's usually how we do reactions, right? We dissolve that in water. Otherwise, how do you get them to mix? It's hard to get solids to mix together, right? But if you dissolve it in water. So does everyone remember that symbol AQ? What does that stand for? Dissolves in water. What's the actual word? Yeah, very good. Aqueous. And aqueous means dissolved in water. So when they react on the other side, we said we're going to have lithium nitrate. So we have to figure out a formula for lithium nitrate. Lithium wants to lose how many electrons? 1 is correct. And that means that a single lithium would give away 1 electron, 2 would give away 2, 3 would give away 3, blah, blah, blah. And we already said that when it forms nitrate needs to take how many electrons? 1. So one of them would take 1, 2 of them would take 2, 3 of them would take 3. What's the formula for lithium nitrate? Great. And that's also soluble in water. All nitrates are soluble in water. You don't have to know that yet. You'll know that eventually. But for now, we'll say that that's going to be a solution as well. And what happens to the copper? It's just by itself. Will it have a charge? No. Copper metal by itself won't have a charge, right? It'll get its electrons back if it's going to form into solid copper. So it'll just be Cu, and it will be a solid. All right? And I'm going to quickly, not that we would always do this, but just right under this, that is that copper 2 nitrate reacting with lithium to form lithium nitrate. Why don't I have to call this lithium 1 nitrate? Yeah. Okay, so there's only 1 charge it can have, so we don't bother listing it, right? We only use the charge form there. Are we done? I think we're done. What aren't we done? What aren't we done? What kind of sentence was that? It needs to be balanced. Good. What do we need more of? Copper, I have 1. Copper, I have 1. Nitrate, I have 2 over here, right? And how many do I have over here? So can I just do that? Why not? That would be a lot easier. Why can't I do that? Very good. Yeah, that would change the actual chemical composition of lithium nitrate, which I can't do. I just need more of them. So where's the 2 go, obviously? In front. That's great, except that breaks something else for me. What's broken now? Which I can solve by doing what? Just adding the 2 in front. A reminder that I did put a little practice module up, and I wanted to, if this is giving you trouble, if you go to Unit 2, I actually made one that's just atom counting. And you can have it sort of make for difficult things. And we can include even a coefficient in front to help you count, right? So if we had 6 gold silicates here, right? If there's 6 of them, how many golds does each one have? 2. But then we have 6 of those, so how many golds do we have total? 12. How many silicons would we have if we have 6 of these things? 6. And then each one of these has how many oxygens? But we have 6 of them, so how many would that be? 18. So if that's something that gives you trouble, you can practice away at that. Does that make sense? Just to make sure that you can kind of accurately tell how many atoms there are. And then once you're kind of comfortable with that, you could go into the balancing practice, where this, you don't have to come up with the reaction. You just have to balance it. And then once you're comfortable with that, you could go to predicting and balancing reactions and you could say, give me single displacement, and it will make single displacement reactions for you all day long, and you can come up with them and balance them. Does that make sense? And when you want to get a little harder, right now, it gives you the formula of what you're starting with. When you're feeling more confident, you can tell it to just give you names, right? So that you're a little bit more challenged. So I really encourage you to use that practice app to sort of practice any of these skills if there's something you're having trouble doing, right? Like if you have trouble going from the name copper 2 nitrate reliably to that formula, go back to Unit 1 and do that practicing, right? Practice it till you're good at it. How's that feel as a double displacement reaction? Or a single displacement reaction, rather. Good? Makes sense? Can I have you guys do one? Let's do exempla gratia due. I don't know. What if we did iron 3 carbonate reacts with, and let's make it, let's say beryllium. I haven't used beryllium in a while. So you can use the one above as a template if you like. If you're not sure what to do, don't sit and do nothing. Talk to your classmates, use your peers, work on it. We'll give you 3.5 more minutes.
The other one has to charge a 2, right? Okay. Okay. So like we choose this, right? Because if we I don't.
Yes.
Okay. And then powers we because there's 3 here, don't we just put 3 in one here?
Yes. But then you'd also need a 3 in the Boolean there.
So is that it?
Yeah. I think
All right,
that's what I did.
can we take a look at this, please? Or do you need a couple more minutes? Oh, take a couple more minutes. Don't let me rush you. Yeah. I do, yeah. Where is it? It is right here. There you go. You're welcome. But you know what? I think I burned through them. You are welcome to go to the office again if you like. Ah. That's not how that goes. Anyway, all right, let's take a little look, shall we? So when you're doing any of these again, we've got to work out formulae for each of them. What is the formula for iron 3 carbonate? Well, in this case, iron is going to give away how many electrons? 3, which means that a single iron, of course, would be able to give away 3. 2 irons would be able to give away 6, 3 irons, 9, etc., etc. And carbonate, what is the formula for the carbonate ion? Yeah. CO3 negative 2. Good. Which means that in forming one of them, thank you, would take 2 electrons, 2, 4, and 3 would take 6 electrons. What is the formula for iron 3 carbonate? Yeah. Very good. Yep, excellent. And we're going to assume that that's aqueous. I'm not sure if that would even dissolve, but we're going to assume it for now because it doesn't really matter. What's this reacting with? Beryllium. And there it is. And what's that going to give us on the other side then? Yeah, we're going to have beryllium carbonate. And so to do that, we need to figure out the formula of beryllium carbonate, right? So to do so, beryllium wants to give away how many electrons? It wants to give away 2 electrons. Carbonate, we said, wants to take 2. So I actually don't need to do any fancy-dancy work here. What's the formula of it? Yeah, nice, easy one. And what will be by its lonesome self? Iron. Good. So just like that, and we're good to go. Oh, I guess we have to balance it. What do we need to do to balance it? Yeah, Bradley Groot. We do need 3 carbonates. So where could I could put that here? Sorry? Yeah. I don't know, because I'm a science teacher. I'm a teacher. Respect my authority. Does anyone else have a problem with my Fe2? Yeah? What should it be? Fe? Fine. How do we balance it then? If it's not Fe2? Yeah, very good. We put 2 in front. Very good. And are we balanced now? Not quite. What do we still need? Got it. And now we're balanced. You mean no, we're not balanced? True or false, that's balanced? False? True, it's balanced.
No, but it's not. Yeah, you have to put it like there, like the front, like lower.
Okay, deal. There we go. There we go. And we're nicely balanced. Why can't I just make it Be3? Why can't I make it Fe2? No, that's not why. Why not? Yeah. Yeah, because it's not diatomic or triatomic, as the case may be, right? Yeah, they don't naturally come in pairs. That's not how they exist, right? So we need this to match physical reality. And we'll assume for the time being that this will be dissolved in water, and metals don't dissolve in water, so we'll assume for the time being that that'll be solid. Good. Now, the anion can also be displaced. Bless you. Let's do, I don't know. Let's do aluminum bromide reacting with fluorine gas. All right, go ahead and do that. Aluminum bromide is going to react with fluorine gas. I would love to. How's that? Wondershun.
So there's 2 though. Okay.
All right. Can we take a look here? Aluminum bromide, what's its formula going to be? Aluminum wants to give away how many electrons? 3 is correct, which of course means that one of them would give away 3 electrons, 2 of them would give away 6, 3 of them would give away 9, etc., etc. Bromine, how many electrons does it need to gain? Uno, si, bene. So 1 would take 1 electron, 2 would receive 2 electrons, 3 would receive 3. So what is the formula here? I have to be honest, I couldn't hear a word you just said. AlBr3. Good, very good. And what do we have this reacting with? Fluorine gas, which is, of course, F2. Very good. In this reaction, what will the outcome be? The bromine isn't, or the aluminum isn't going to get replaced by fluorine, right? You can't have something that gives away electrons be replaced by something that takes them, right? It can react with something that takes them, but it can't be replaced by something that takes them. Something has to give the electrons. Is fluorine going to give electrons to bromine? Absolutely not. But what will happen is that fluorine can kick bromine out. So what will be by itself on the other side? Bromine, which of course will take what formula? Br2, because it's one of our diatomic elements. And then what would the compound here be? Well, it will be aluminum not with bromine, but aluminum with fluorine, which of course will look exactly the same, because aluminum still is going to give away 3 electrons when it forms this compound, right? But fluorine also takes just 1 electron. So the formula of aluminum fluoride is Al, I want that to color match. AlF3. And then to balance this, fairly trivial. Yep. Yep. On both sides, right? Yep. Good. And then what do I have to put in front of here?
3.
Yeah, very good. Yeah, excellent job, guys. How's that feel? Not too bad? Yep. Why is there 2 after what? Because fluorine is one of our diatomic elements, which reminds me, everybody stand up. Everybody up. Everybody up. Let's all stand. Because, of course, team, lest we forget, and listen, this could go quickly or it can take a very long, sad time, all right? What are the diatomic elements again? Oh, okay. Bad. Guys, team. Team, do I have to go? All right. Well, let's do things. Team, what are the diatomic elements?
Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine.
C+, very good. Sit down. Oh, you know what? We'll give that a B. That's a B minus. That was good. All right, that was pretty good. That was pretty good, team. Yeah, so it's one of our diatomic elements. So whenever we see hydrogen, oxygen, fluorine, chlorine, bromine, or iodine by themselves as elements, they'll always be written as F2, Br2, Cl2, H2, etc., N2, O2. Cool. Now, this, of course, raises a burning question. And we'll use a simple example, right? I'll use a nice 1-to-1. If we had, I don't know, let's say hydrochloric acid, and we put sodium in with it. Actually, that's not the example I want. I changed my mind. Guys, I changed my mind. Let's say we put potassium chloride in, and we react it with sodium. I picked this because everything's a nice 1-to-1. Potassium likes to give 1, sodium likes to give 1, chlorine likes to take 1, right? Nice and easy. What would the product be? Go. Okay, so sodium chloride and... Okay, great. Does that make sense? Okay, so we're going to take that as a given. If we know that's true, what about sodium chloride plus potassium? What then? Well, presumably, what will it form? Well, wait a minute. Plus sodium. So which one's true? Are they both true? Because how could you ever actually get one to happen if as soon as it happens, it unhappens? So which one of these is true? Did you think about that before? Which one's true? How do you know? This is the grade 11 wrinkle. How do you know? And the answer is we had to do experiments. We had to test in a lab which reactions happen and which don't. And we ended up with, we found a trend. Called activity, or the activity series. And I'm going to copy and paste one in here. And it doesn't really matter which one we use. For now, we're just going to put a relatively small one, right? And then later on, I'll give you a handout with a more robust one. You can look up a full activity series online. There's a graphic out. There's a nice, easy one I like. Well, for goodness sakes. Oh, I have it in here. You guys have to write it, but I'm going to cut and paste. Yeah, listen, with age comes privilege. I'm an old man. You can't expect me to write. Okay, so there we go. This is the activity series. You can take a minute and write that down. Oh, yeah. Speaking.
She's not in this class. You're gonna have to wait for the next class. She's looking for automaton. She's not in.
Thank you so much.
She ran away. I mean, she did glitch out too, so.
Did she? Oh, no.
Sounded a bit robotic.
Maybe she's been replaced by an AI. Maybe that was attendance GPT.
I do know that it is somebody filling in for Miss Alex.
Yep. I can always understand Miss Allen now. I've got her, like, even on that crappy PA that is blocked by my fume hood, so I can't really hear it. She's good. She's got a very clear... Ms. Mamalidi I struggle to hear, but Ms. Allen I've gotten good. She also just pages me a lot, because it's like, hey, idiot, do your attendance.
Like, they're on a phone, so they go to, like, that customer service, like, you know how they're always speaking on the phone, so they raise their voice.
Has anyone ever worked at a job where you have to answer the phone a lot? I guess that's less a thing in 2025, but still. But when I pick up a phone, I still have to restrain myself from saying, fine kettle fish, how can I help you? Because I must have said that, like, what do you actually, probably 10,000 times? I worked there for 11 years. I probably worked an average of 4 days a week for 11 years. Okay, well, you guys are doing this. I'm going to do a little math. That's what I'm going to do. 11 years, 52 weeks. Say I took a week off a year, probably. 4 shifts a week. I probably answered the phone 10 times a shift. So I think conservatively, I probably said that about 22,440 times. That's a lot of times. So now, while you're writing it, what this list does is it tells you the most reactive metals to the least reactive metals, and basically, a metal has to be higher on this list to be able to displace something. Does that make sense? So, oh, and not just a metal, also for chlorine, fluorine, bromine, and iodine. A species must be higher, or I'm going to say an element must be higher on the list. Fun fact about the word higher, it has an H after the G. So if we go back to our burning question, which of those reactions does happen? In one, we had potassium chloride reacting with sodium to form sodium chloride and potassium. In the other, we had sodium chloride reacting with potassium to form potassium chloride and sodium. Which one of those reactions actually occurs? Right? So you got these two reactions. So for this reaction to occur, sodium would have to be higher on the activity series than potassium, right? Is it? Let's go check. Potassium is here. Sodium is there. So is sodium able to kick out potassium? No. So this reaction actually doesn't happen. On the other hand, this reaction, potassium reacting with sodium chloride, is potassium able to kick out sodium? So these aren't two reactions that endlessly go back and forth. The bottom one does happen, and the top one does not happen. Does that make sense? So would they react? Sorry? Not at the moment, but yeah, when I'm done, absolutely. So just quickly, will those react? Yep. What did I do? Oh, I'm sorry. No, that should be iodine. I blame my bovine spongiform encephalopathy. I have mad cow disease, I'm convinced. I'm convinced that my brain is slowly becoming spongy. My evidence for this is that every day I seem to be a little bit stupider than I was the day before. No, but it's true. Like, listen, I wish it were a horrible comment. It's just a description of my mental faculties. It's very upsetting. Yes. Chlorate. in this case. And you don't actually have to do these reactions. I just want to know, will they react? Sorry? Yep. What? Okay, this first one, AU. Gold is gold, right? And we're asking if it would react with AgCl. What's Ag? Silver. So will gold be able to kick out silver and cause a reaction? Why not? Yeah, if we look on this list, gold is the least reactive metal we have. So it's not going to be able to kick out anything. This, by the way, is why we make things that we want to last a long time out of gold. It is highly non-reactive. It doesn't like to react with things. It's very stable as its own thing. All right, what about iron with zinc sulfate? Would iron be able to kick out zinc in zinc sulfate? Okay, no reaction. Very good. What about tin and mercury chlorate? Yes. Which, by the way, means what would the products be? Just name. We don't need to worry about the formula. Tin, chlorate, and mercury. Very good. By the way, there's no such thing as mercury chlorate by itself because mercury is either mercury 1 or mercury 2, so we'll make it mercury 2 chlorate. That's a bad question on my part. Not that it matters. Note, by the way, that's not mercury 2. It's not the ion, right? It's just mercury. How's that? I'm going to put some digital practice up today, which will do both. It will give you an opportunity to first just predict, will they react? So like, I don't know, let's take a look right now. They won't necessarily all be on your list. If they're not, just skip to a new question for now. Will solid gold be able to react with aqueous nickel 2 nitrate? Good. Will copper be able to react with manganese iodide? Will copper be able to react with manganese? Is manganese on your list? No, magnesium's on your list, but manganese isn't. So we'll skip that for now. Will zinc be able to react with strontium? Boy, I put lots of things on here that you don't have. I might quickly modify that to limit it to your list for now. I'll do that during the break, just so you're not going nuts. But then there's also going to be practice where you actually have to predict and balance the outcome. And we'll set it to single displacement. And you guys can come in here. You don't need me to give you practice, by the way. You can do this. In this case, it'll always give you ones that actually work. Does that make sense? You don't have to worry that it's going to give you non-existent ones. So this solid copper reacts with mercury 2 thiosulfate. And by the way, you might not know, we might not have seen thiosulfate before, but that's okay. Can we figure out from this what the charge on thiosulfate must be if mercury has a charge of +2? What's thiosulfate got to be? If the mercury is giving +2, what must the thiosulfate be giving? -2. And if you didn't know that, that's okay. You can go to the periodic table here. If it'll load periodic table. And one of the things you can do is you can go to ionic charge, and it gives you a list of all your things here. So you can see thiosulfate is S2O3 -2. So you don't have to know them. You always have the periodic table here, and you always have ionic charge there. But so on the other end, we'll get what? What will be by itself? On the other side, what will be by itself now? Sorry? Mercury is right. And what will be the compound here? Will be copper thiosulfate, and it tells us to use a 2 plus charge, and it has a 2 plus charge, and thiosulfate has a 2 minus charge. So that's actually easy. CuS2O3. And is that balanced? I think so. 1 copper, 1 copper, 1 mercury, 1 mercury, 2 sulfurs, 2 sulfurs, 3 oxygens, 3 oxygens. Should be good. Right? So you can plug away at those so you can get practice making these predictions. Yeah? Yeah, boy, this will not play nice on your phone. On your phone? Yeah, don't try and use this on your phone. I would love to be a good enough coder that I can make this play nicely on your phone, but this just really, it's just not the right place to be trying to do this, you know? Get a laptop, get a computer. If you need to borrow one, come talk to me. You're more than welcome to borrow one.